Hello friends, for all part of globe, good morning, good afternoon or good evening. This is Abhigya Saxena from Noldas Software. I am AVP Engineering and enjoying my responsibility of taking care of Java Studio for the organization. I am thankful that you are here. I will try my best to explain the topic rightly and concisely. I really hope that you will enjoy the session. So let us begin. Before we start with the core topic, let me share some information about Noldas. Noldas is a technology consulting firm with focus on modernizing the digital systems at the pace of your business demand. Started in 2010 with the actively be on the edge of the latest technology. Quickly become partner with Lightband, Databricks, Confluent, DataStack, Docker and IBM. Noldas keeps customer ahead with the future-ready technology and their processes. Collaborating with Noldas means collaborating with the technology. Yeah. So let us begin with our core topic. As mentioned, this webinar is dedicated to microservices design pattern. So first let us understand what we are going to cover during this session. Introduction. In this section, I will make you aware about scope of this webinar. What is microservices? Core topic is design pattern for microservices. So it is obvious that we need to first understand microservices in a very brief manner. What is design patterns in microservices? Here I will explain what is design pattern in context of microservices. Which design patterns are for microservice? From here, our core agenda will be kicked off. I will start explaining all the design patterns in this section under mention 5 broad categories of design pattern. Those categories are decomposition patterns, integration patterns, database patterns, observability patterns, and cross-cutting patterns. Tools and technologies. Here, I will mention associated tools to fulfill interest of few design patterns. Here I haven't addressed all the design patterns which I am going to explain you in section 4. Closure. This is going to be a routine closure section where I will summarize about webinar. Introduction. This webinar will cover theoretical aspect of the design patterns in microservice. So we haven't considered any demo for any design pattern. The effort is made to share knowledge in a way so that you can understand the kind of problem particular design pattern solves. And it will trigger your knowledge with respect to the design patterns in microservices. Effort is also made to cover advantages, disadvantages and challenges with respect to few design pattern. For selected design pattern, I have mentioned advantage and disadvantage and challenges. For certain design patterns, I haven't considered any of these parameters because either they are self-explanatory or insignificant. Brief information of tools with respect to few design pattern are also considered over. So I have listed few tools for few design patterns. Here I haven't considered all those design patterns which are of type strategy instead of technology implementation. So there are always certain design patterns which does not require technical implementation, but they are more towards operational level. So I haven't considered those design pattern with respect to listing the tools. Code level implementation is not included due to the time constraint. Yeah, so it is very obvious and very obvious expectation also to have some kind of code implementation to put a demonstration of effectiveness of design pattern. But yeah, because of time constraint, I have considered that part. But in future, there are a lot of chances that I will cover this part in a separate webinar. What is microservices? It's an approach, design pattern and an architecture all at a one time. Microservices is a way of dealing with situation or a problem. Obviously, those situations and problems are with respect to the monolith implementation. A design pattern is the reusable form of solution to a design problem. That is something a conventional definition of design patterns. I mean to say standard solution to a standard problem. And so far as architecture context is concerned, the tools and techniques to design the building application. So in microservices, obviously we are having tools and techniques to develop and implement functionality in right way and at granular level. It's a granularized implementation of any functionality. Granularization means decomposition of bigger implementation. That decomposition happens with respect to functionality, with respect to capacity of processing, with respect to domain, with respect to transaction, with respect to subdomain. So those are the parameters through what we can break down our monolith implementation to a granular level implementation in so many pieces. Granular implementation helps us to achieve maintainable and testable piece of code. For a developer, maintainable code simply means code that is easy to modify or easy to extend. And it should be well encapsulated and in charge of its own state. Here, how we can achieve a code which can be modified easily and which can be extended easily. In this scenario, if we manage to develop code in logically smaller size with sharp definition of input and sharp definition of output. In this scenario, we can have very much scope of extension. Also, if we have sharply defined inputs and output, we can have right strategy of achieving right testing approaches. So in microservices, having code maintainable and testable, that means we should have a right small size of code and we should have sharp boundaries of input and output. This will definitely achieve our capacity of testing and capacity of maintaining the code. Loosely coupled implementation. It's an essential principle of microservices architecture. If you ignore this principle and develop tightly coupled services, the result will mostly likely be yet another microservices failure story. Your application will be brittle and have all of disadvantages of both monolith and microservices architecture. So if you miss right approach with respect to loosely coupled implementation, I think you will land in trouble more bigger than monolith implementation. Deployment autonomy. Independent deployability is the idea that we can make change to microservices and deploy it into production environment without having to utilize any other services. This is, I think, with respect to isolation also. So independence comes when we will be able to manage right isolation. To guarantee independent deployment ability, we need to ensure our services are loosely coupled. In other words, we need to be able to change one service without having to change anything else. So as I mentioned, deployment always go with the isolation, and isolation will go with the loosely coupled implementation. Agility. Agility is capacity to support fast development, quick scaling, and rapid deployment. And all these are supposed to be part of microservices implementation. Technology agnostic approach. Yes. So here we want to get rid of binding with particular technology. We can have same functionality implemented in different technologies and different functionalities in different technologies. I mean to say, we can have same functionality implemented in different technology in different deployment strategies. Similar way, we can have different functionalities implemented in different technology also. And that too either in same domain or in same subdomain. Here, through this approach, client will remain unaffected with respect to expected result. So we should be very much sure if we will use different flavor of technology for same functionality or different functionality, the client should not be affected with any adverse effect. Scalability is ability to increase or decrease capability of processing, load handling, storage, or many other parameters. In monolithic architecture, we are having such capacity, but in terms of vertical only. While in microservice, we can scale up and scale down vertically as well as horizontally. So here we are having one more dimension where we can manage scalability. What is design pattern in microservices? Design patterns are solution to standard problems. In microservices also, they are solution to standard problems. Normally, there are few principles considered while solving the standard problems to achieve anticipated architecture. Those principles are independent autonomous services. Independent autonomous with respect to what? Definitely those parameters like development, deployment, execution, operations, maintenance. So those are parameters supposed to be have their independency as well as autonomy with respect to operations. Scalability. Scalability, yes, horizontal as well as vertical in context of processing power, in context of load, in context of availability, or in context of storage as well. Decentralization. So decentralization, and this means it should be distributed in context of region, in context of availability zone. So those are so it should not be that the whole infrastructure is at one place and entire world will access those features from one region of globe. So it should be decentralized. Resilient services. So this means the robustness supposed to be there with on adverse conditions for the services. Real-time load balancing. Yeah, this means load balancing again with respect to processing, with respect to number of requests, or with respect to storage. So for example, at some point of time, at particular services number of requests increases, then the infrastructure is supposed to respond those number of requests in a way so that each service will have equal amount of requests. So there should be threshold supposed to be managed with respect to the number of requests for particular services. So in that scenario, load balancing is required for each and every services. So the load will be distributed among all available services. Availability is something which is in terms of any service, whether it is down, whether it is not responding, or availability with respect to region specific. As we have already mentioned the parameter of decentralization, so for each region the service supposed to be available. For each adverse condition, the other service is also available to cater the request of client. Continuous delivery through DevOps integration. Yes, so any changes implemented that should be delivered at production environment, and all the changes supposed to be integrated with the existing deployed application. Seamless API integration, continuous monitoring. All the parameter with respect to health, with respect to logs, with respect to fault, they are supposed to be monitored, and they are supposed to be responded with respect to right seamless integration. Isolation from failure. So if some adverse condition fails, any services are not available, there is some latency issue, there is some issue with respect to load. So in that scenario, one service supposed to be isolated with respect to the failure of another service, or if some services fail, then in that scenario the diversion of request supposed to occur in a way so that the failures or fault will be isolated with respect to the response to the client. Auto provisioning. When we are thinking about scalability or decentralization, so in that scenario the resource provisioning supposed to be automated, in terms of if we need more resources with respect to request, there are new service supposed to be added. If we need some kind of services in some kind of region in more quantity, then those kind of provisions supposed to be automated. So these are the principles which are supposed to be followed when we are considering design patterns in microservices. Which design patterns are for microservices? Here we have reached exactly at the position from where our actual subject will start. Generalization of microservices design patterns can be done in 5 categories. The first one is decomposition pattern. This pattern is considered right from when we have started thinking to migrate from monolithic to microservices architecture. In other words, I can say these are evolutionary patterns from breaking down your monolith to microservices. Now, breaking down in which context? So such design patterns provide approaches for breakdown functionality, continuum while migration, traffic management or quantifying the traffic. And fourth one is utility separation. Now, breaking down functionality, how? That is with respect to domain, that is with respect to subdomain, or that is with respect to kind of transaction. Continuum while migration. When you are migrating from A to B, you need to be cautious with respect to the availability of application to the client. So during the progression of migration, this pattern will guide you how we can pick the approach. Traffic management or quantifying the traffic. So here the quantity of traffic will be decomposed in a way so that each and every services will get the load equally or in a logical quantity. Fourth one, utility separation. Every application has two aspects, functional and non-functional aspect. So this separation is getting handled in this kind of design patterns. Now, let us move to the next category of design patterns. that is integration patterns. Now, after decomposition of monolith implementation, we will have microservices implementation at different location, and they are physically separated by a network and need to communicate with each other as well. So this type of design pattern helps in choosing the approach of integration that will offer the most autonomy and scale. So what does that mean? When services are scattered at different location and getting communicated through network, in that scenario, to achieve some functionality, we may require to collate more than one services, or in a different word, to achieve business purpose, we may require to utilize more than one services. So this approach is integration of or aggregation of services. Now, where this aggregation happen or where this integration is required to be implemented. So the scope of implementation of integration or aggregation may be at the entry point of request, or it may be at the leaf level services of implementation. So it may be at gateway level, or it may be at the last services which is getting called to fulfill the business functionality. Let us move to the next category of design patterns. This is database patterns, and these patterns addresses most important concern in database design in microservices architecture. Especially these patterns provides approach for how to store data and where to store the data. In microservices app, data ownership is decentralized in contrast to monolith implementation, and so different approaches are needed for database management. Yes, so think about how transaction will take place when for one transaction there are number of different databases, or if each microservices update its own database and another microservices service updates its own database. So imagine what kind of complexity we need to take care while we are dealing database activity in microservices architecture. Approaches for challenges in asynchronous microservices architecture can be found in such design pattern. Let us move to fourth category of design pattern: observability patterns. These patterns provide the solution with respect to non-functional requirement of application. Logs, matrices, and traces are often known as the three pillars of observability. Design patterns under this category provides the approach to achieve these goals. In monolith system, the scope is single process, while in microservices architecture, we may have to jump through many services and network boundaries. So this has some more complexity than monolithic architecture. Managing parameters for service level objective is difficult over here, because maintaining logs, matrices, and tracing, they are not limited to at one location or at one implementation. Now let us move to the last category of design pattern, that is cross-cutting patterns. Cross-cutting concerns are generic functionality which are not related to application's business logic, but they are needed in many places. Managing configuration, making fault tolerant, maintaining continuity, maintaining service catalog, etc. are concerns which are being addressed by this category of design pattern. Though this category of design pattern are not directly related to business functionality, but you cannot escape without implementing these design patterns in your application, because if you won't implement such approaches, you will not find the robustness and stability in your implementations. Let us start deep dive in each category of design pattern. So first we have considered decomposition patterns. Decomposition patterns has 6 different design patterns, and the first one is decomposed by business capability. This helps to decouple organization with respect to business capability. So the problem area which this design pattern addresses is that how to decouple organization on the basis of business capability. A business capability defines what a business does at its core. We should define microservices corresponding to particular business capability. For example, sales, customer service, or marketing. An organization's business capability are identified by analyzing organization's purpose, structure, business processes, and areas of expertise. Now, you understand, application design is tightly coupled with business model, and so in-depth understanding of overall business is required. It can be difficult to identify business capability and services if we are not having enough understanding of overall business. A business capability often corresponds to business objects, like order management is responsible for orders, customer management is responsible for customer. So here objects are orders and customers. Now let us move to second design pattern under this category, and that is decomposed by subdomain. It addresses problem of breaking down large application into small loosely coupled services. Here term domain refers to business. All businesses have subsections which can be termed as a subdomain. If we are considering retail as a domain, associated subdomain can be order management or customer management, etc. This approach is a domain-driven design. This approach breaks down the organization's domain model into separate subdomains that are labeled as core, that is key differentiator for business, supporting, possibly related to business but not differentiated, or generic, not business specific. This pattern is appropriate for existing monolithic system that have well-defined boundaries between subdomain related modules. So as I discussed, if we consider retail domain, then order management and customer management can be considered as a implemented module in monolith architecture. So when we are thinking to break down this implementation on the basis of subdomain, we can consider we need to break down this implementation by considering order management as a one subdomain and customer management as second domain. Here we can consider some advantage of this approach. It is highly stable if business of this subdomain are stable. This support technology agnostic approach and organized functional features. As segregated on the basis of subdomain, services are highly loosely coupled. So we can get all the benefit with respect to isolation and independence of services with respect to each other. There are some challenges with respect to this design pattern. to implement this design pattern, we need to have good understanding of business. It is obvious that unless we will not have understanding of business, we won't be understand the difference between domain and subdomain. We cannot define boundaries of subdomains rightly and sharply. Second challenge over here is high level domain model has to be clear and it is required. So as I have taken example with respect to retail domain, where we have considered order management and customer management. Here, if we are not clear with respect to the domain under which this domain are falling, or we do not have clarity of domain, then all the strategy what we are going to define for breaking down this application will not be as effective as expected. Let us move to third design pattern, that is decomposed by transaction. This design pattern is an approach to complete one business transaction by avoiding latency issues or two-phase commit problem in microservices. In distributed system, an application typically needs to call multiple microservices to complete one business transaction. Right? To avoid latency issue or two-phase commit problem, you can group your microservices based on the transaction. Right? And this grouping can be done on the basis of transaction characteristics or its generalization. So if we consider example, then grouping can be done on the basis on data of sales, customer, compliance, and marketing. So we have decomposed transaction with respect to generalization of transaction, right? So similar way, there are chances we can find another category where generalization can be done for the transaction, and we can segregate those transactions with respect to another category of transaction. So advantage of this design pattern is faster response time. Why? Because we have decomposed the transaction instead of we have coupled them in one microservices or in limited microservices. Improve availability. Yeah. So now we have decoupled transaction on the basis of characteristics or generalization. We will have more number of microservices to cater the transaction functionality. So we will have more availability of services. There are some challenges in this design pattern also. Multiple modules can be packaged together, which can create a monolith. So again, here architect has to be enough sensitive with respect to the categorization or with respect to decomposition. Inconsistent version might be deployed at same time for the same business domain. Yes, this is something related to version control mechanism and mostly with respect to DevOps activity. But if such kind of error happens in with respect to deployment, or if you are not able to manage the version, in that scenario there are a lot of chances where the ambiguity of services will be there. So this may make the implementation inconsistent. Now let us move to fourth design pattern under this category, that is strangler pattern. This comes in picture during migration of legacy monolithic application to microservice architecture. Design pattern is to incrementally transform your monolithic application into microservices by replacing a particular functionality with new services. One can develop a new component and let both the new and old component exist for a period of time and finally terminate the old component. Adopting the strangler pattern to gradually migrate into a new system reduces the risk of complete failure, because we are terminating the old component only when we are having working component in our new microservices architecture in a production environment. At certain point of time, multiple implementation are exist for the same functionality. We can get rid of challenges of accessing multiple applications by creating a right routing facade. Right? Exact approach of implementing strangler pattern will differ for each monolithic implementation, but generally it starts with most simplest component to most complex component. Now let us discuss about the advantage and challenges in this design pattern. The advantages are end user never feels any downtime for any functionality while migration. Another advantage, anytime switching between new and old architecture can be done if situation demand. And so smooth decommission of old architecture can be done. Let us talk about some challenges. If migration components are not defined or picked wisely, there will be operational challenges. So as I mentioned, generally it starts with most simplest component and goes with the most complex component. So if similar kind of approaches we haven't selected wisely, then I'm sure you will end up with lot of ambiguity during the migration phase. As old architecture will remain exist mostly till complete migration, organization has to bear cost of infrastructure and resources till the end of migration, right? So this is little bit cost intensive migration. The fifth design pattern under this category is bulkhead pattern. Overpopulation of requests to any service will lead to malfunction state for the service. These design patterns aim to allocate certain limit on usage of services. So it decomposes quantity of traffic with respect to service or services. So what does that mean? This means if any service deployed on an infrastructure which can handle or which can support up to 500 requests per second, and at certain time the request count goes to 600, 700, 800. In this scenario, the client has to wait till the 500 request completes and it starts picking over the 500 request. So in this scenario the request will be blocked and client has to wait. To overcome this problem, the cap of 500 requests per second can be managed, and if 500 first request comes, then that request diverts to another available services which has same implementation. So here the latency is getting managed with respect to putting a cap of certain limit, right? So microservice will not entertain any request which is more than 500 in particular second, right? This design pattern is influenced through bulkhead implementation in boards and ships. where one chamber stops flowing water to another chamber and prevents sinking, right? This pattern is to achieve fault tolerance against the quantity of requests to particular services. So what is the advantage of this design pattern? This acts as load balancer, and so performance can be managed consistently across all the deployment. So the worst performance comes with respect to particular services if the service reaches to 500 count, request reaches to 500 count per second, but after that if new request comes, then it diverts to another microservices. That means we are managing a certain level of latency consistently, right? So this is something related to performance achievement. Now what is the challenge? If request limit is not set with the right strategy, inconsistent behavior will be observed, right? So for this is in connection of number of microservices available for particular functionality and the quantity of traffic. So we need to balance this balance the number with respect to the limit of handling capacity that should be connected with reference to the infrastructure where the microservices it's deployed. So we need to be cautious with respect to the architectural decision for limit. Okay. The last design pattern under this category is sidecar pattern. Separation of core functionality with non-functional utility implementation is core purpose of this design pattern. The sidecar provides the supporting features to its parent application, and in turn it reduces the overall complexity. What does that mean? This means if your implementation is like functional and non-functional code at one place, that will lead to complex coding approach or complex implementation approach, right? So here the separation between functional implementation and non-functional implementation is implemented or considered. In other words, separating cross-cutting operation from microservice to reduce its internal complexity. For the core functionality, cross-cutting needs can be logging, messaging, monitoring, etc. So how it is getting implemented? The cross-cutting implementation is implemented through certain microservices, and functional related implementation is done in certain microservices, and this non-functional related microservices go along with the functional related microservices. So as and when the non-functional requirement is there, the functional microservices utilize this sidecar microservices. Sidecar microservices are nothing but they contains non-functional implementation of application. Now what are the benefit of this design pattern? As we discuss, it reduces the complexity in microservice code by abstracting the common infrastructure related functionality to a different layer. Reduce code duplication in microservices architecture, since you do not need to write configuration code inside the microservice. Provide loose coupling between application code and the underlying platform. Now what is challenge? Here challenge is with respect to we should be very much clear about non-functional requirement and its required scaling, else it will end up in incorrect resource utilization. This is something related to an architectural call, right? So this parameter supposed to be taken care when actually we are implementing this approach. Now we are done with the decomposition patterns. So let us jump to next category of design pattern, that is integration patterns. So integration patterns contains 7 different design patterns. The first one is API gateway pattern. As your application grows in size and complexity, it gives challenges while calling microservices. Those challenges can be performance issues, scalability issues, security issues, or complexity issues. So this design pattern addresses problem of handling complexity while calling microservice. API gateway is approach to handle such parameter. It provides an extra layer, a single entry point between a group of microservices and the front layer. It resembles the facade design patterns where we have one entry point for rest of APIs. All the configuration or plugin attachment done within this layer to manage above mentioned challenges. The advantages of this design pattern are, with a single request response, required set of microservices can be called. Second advantage, it can provide one-stop management of cross-cutting concerns. As I mentioned, we can attach plugins or we can manage configuration through this layer. It isolates clients from thinking about how the application is divided into microservices. So for a client, there will be only one call, and underlying this one call, there are n numbers of microservices plays their role. So for client, there is one call, and functionality can be achieved by considering many microservices behind the scene. Now let us understand the challenges with respect to this layer. Since the API gateway will create an extra layer, it can cause an increase in time with negligible difference as a result of request. So this is not that significant if we have really mess up the implementation. So in normal scenario, the delay is so negligible that even we cannot feel that. The second challenge, since the access to all services through the API gateway, the entire system may fail in case of any breakdown or any interruption occur. So we are considering many microservices on the basis of one call. So that call will be affected even a single microservices service malfunctions. So this is sensitive, but we need to implement right strategy with respect to such scenarios. Let us move to next design pattern under this category. Aggregator pattern. As services are relatively micro in size and typically a microservice implements a single task, distributed and decentralized multiple services need to be identified and aggregated to serve a full-fledged business functionality and feature. This means to achieve a functionality, we need to call multiple microservices, because each microservices have small chunk of tasks, and by calling more than one microservice that is required to fulfill microservices, that will require some aggregation. Now, aggregator design pattern is a service that receives a request, then make request to multiple services, combines the result and responds to initiating request. Same way. So we are combining result of more than one microservice to achieve particular functionality. Aggregation of service call happens at gateway level. The advantage of aggregator patterns are reduces calls and communication overhead between the client and services. So it is pretty simple. So if we are not aggregating microservices, client has to call more than one microservices to fulfill business functionality. The second advantage is allows for architecturally easily understood endpoint consolidation of discrete functionality. Yeah, so it is same. So we have sharp endpoint to fulfill one functionality, even though this functionality contains more than one task, or this functionality require more than one microservices to achieve the functionality. The third advantage, it can work like a proxy that will forward requests to relevant services. Yeah. Here the actual services are not exposed to client. So we are calling one service that means a gateway, and gateway will take care of aggregating all the tasks. So eventually we are hiding actual microservices from the client. So gateway works as a proxy. There are few challenges in this microservice. Reduces availability as a result of multiplicative effect of failure. Yeah, so through gateway we are calling more than one microservices. So out of n microservices, if one microservices fail, in that scenario the entire call becomes faulty, and if the calls are synchronous, then all the microservices which takes part in fulfilling functionality, they gets blocked, and so availability of microservices will reduce. This is a drawback. Likely increases latency of response. Yeah, so we can consider the response will be more. Response takes more time because there are n numbers of services required to be called, and the back and forth call between gateway and services, they consume some time, and so there are chances to have little latency with respect to holistic response. Increased complexity of troubleshooting. Yes, here things gets little bit complex because there are more numbers of microservices. So when it comes with respect to debugging the application, it gives some challenges with respect to complexity, and obviously if complexity is there, cost of time will also be there. Let us move to third design pattern, that is proxy pattern. Proxy pattern provides placeholder or surrogacy for another microservice or services. We create a microservice to invoke other services based on the business requirement. So here we are adding one microservice which invokes other service based on the business requirement, right? So the proxy service can be a dumb proxy service which just delegates the request to one of the service, and there is a possibility of smart proxy where some data transformation is applied before the response is served to the client. So let me give you the example. Let us take a service which takes inputs as a number and it returns square of that number. So now in case of dumb proxy, the proxy service will pick the input from client, it provides same input to original service, and it gets output from original service, that is square of that number, and return it to the client. So there is no change in any functionality with respect to implementation of this proxy. That means it is a dumb proxy. Now let us consider what is the case of smart proxy. What happens in smart proxy? For example, client had provided number n to smart proxy. Smart proxy has reduced that number by 1 and the new value will be submitted to original service. Now original service has received n minus 1 from the proxy service. It has squared that number So n square of n minus 1, and it returned that value to proxy service, and proxy service had returned that value to client. So in smart proxy case, the square, though the number supplied same, that is n, but return type is square of n minus 1. So here the functionality has changed in between, right? So this is called smart proxy, right? So let us understand the advantage of proxy pattern. Security aspect can be implemented through proxy services. So what kind of security aspects? For example, we don't want to expose the original microservices. We want to keep its these services at some safe location, or with some level of authentication or authorization. So we can straight away hide the original microservice, and we can expose some proxy service, and we can achieve some security aspects, right? This pattern avoids duplication of object which might be huge size and memory intensive. This in turn increases the performance of application. Now, what happens if we implement one more service to achieve n minus 1 square of n minus 1? So this is very simple example where the performance difference is not more. But in case of services which consumes lot of resources in terms of memory or in terms of processing activity, in that scenario we cannot afford to create duplicate microservices, right? So that will affect infrastructure. So implementing proxy service will definitely increase the performance holistically, right? Now let us move to the challenges. This pattern introduces another layer of which sometimes may be issue if real subject code is accessed by some of the client directly, and some of them might access the proxy classes. This is very this is actually a very good problem, or this is something which really we need to care of. We need to care of such problem. So what happen? Suppose in same example, if we have proxies for a service which returns the square of number, and client is accessing proxy service, not the original service. What will happen? Someone makes some changes in original service, and client will remain and get exposed to proxy service. So the expectation of client is getting square number, and someone had made the change of original service, and that developer had changed in a way so that instead of square, now cube of some number is returned. So in this scenario, client is not aware of what kind of change has implemented, and still it is client is expecting the square of number. So here the problem occurs that the functionality is implemented in other service, so proxy service cannot control the changes in original services. So here we need to manage changes with respect to the versioning of services in terms of proxy and in terms of original. So they need to go in sync with respect to every changes. As it introduces one more layer of service, incorrect implementation may cause performance related issue. Yeah, adding any layer will definitely affect with respect to performance. I agree on that part. But if we can handle this problem rightly, we can achieve very minimal and negligible performance change. Otherwise things are fine only. Fourth design pattern, that is gateway routing. Gateway routing pattern is to route requests to multiple microservices with exposing a single endpoint. So when the client needs to consume several microservices, gateway routing pattern offers to create a new endpoint that handles the request and route this request for each service. So let us understand this thing through an example, right? This design pattern is to send request to search something in different subdomain. So if we have implemented this design pattern, and through this design pattern we want to send some parameter to search in different domain. Here one request will trigger a service, and this service will trigger all the search services of all required subdomain, right? So this parameter will pass to services of subdomain where search functionality is implemented for particular subdomain or individual subdomain. Once search completes from all the subdomain, the search result will go to routing service, and that routing service will send that result to client. So in a way, client has to call only one service to find particular value in more than one subdomains, right? So this is how it works. So let us understand what are the advantage. It reduces number of count of service requests. Sorry, it reduces number of count of service requests, right? So instead of searching in separately for each subdomain, we have just make one call to a particular endpoint, and we have achieved search result for all the subdomain which we are interested, right? Reduce complexity when functionality requires to call many services to achieve similar tasks, right? Yeah. So we saw it is logical to call one service instead of calling n different services for the same purpose. That means to search something in different subdomain, right? So if we call more services, that means we are giving more complexity to our client. So here it reduces. There are chances of single point failure, as out of all any service fails, endpoint service will be affected, right? So if out of 5 subdomain services, if one service fails, then that failure affects the execution of our endpoint service, and this execution eventually affect the result which is required to send client. Or it might be possible that endpoint fails completely and client will not receive any result. So this is a drawback of this implementation, but with right implementation of strategy can solve this problem also. Let us move to the next design pattern of this category. Change microservices pattern. Here approach is provided to carry out sequence of tasks to achieve functional or non-functional need of application. Chain microservice design pattern produces a single consolidated response to all requests. All these services uses synchronous HTTP request to response for messaging. So here we need to understand client will call one service, that service called to another service called to another service. So this way chain is getting created. So for client end, there will be only one endpoint. The key part to remember is that the client is blocked until the complete chain of request or response. What does that mean? We have already mentioned that all these services uses synchronous HTTP request. That means the request will not come back or control will not come back unless the complete processing gets completed by each and every microservices. Now let us understand what are the benefits. Set of tasks can be achieved through one request. Yeah, as I mentioned, we have only one endpoint, so client will send request to that endpoint, and after that all the required tasks will be carried out one by one. Entire functionality can be carried out a single endpoint. I think this is similar to what we have discussed, right? If chain of microservices too long, client will require to wait for a long, and this delay may cause inconsistency. this is a challenge, or this you can consider as a disadvantage. So being synchronous call, it might be possible, it will take too much time if we have created the chain of bigger size. In that scenario, there are a lot of chances that somewhere session get expire till we reaches back to the client. So this is a challenge, and we need to manage with the implementation of right size of chain. The sixth design pattern in this category is branch pattern. A microservice may need to get the data from multiple sources, including other microservices. Branch pattern can also be used to invoke different chains of microservice or even single chain based on business needs. This pattern is combination of synchronous and asynchronous microservice call. Why? Because as I mentioned, this is combination of chain microservice or a single microservice, right? So single chain based microservice, right? So here, whichever service falls under the sequence call, they are going to be synchronous, and whichever falls in parallel call, they will remain asynchronous. So as it is combination of synchronous and asynchronous calls, it has better turnaround time than chain design pattern. So for example, if branch pattern contains 10 microservices, then there are few services fall in parallel call, and few services will be part of chain microservices. So this will reduce execution time because there are some parallel execution. But what happened if all these 10 microservices are in chain? In that scenario, response will require to wait till all the executions are over. So here I think we can get better turnaround time than simply chain microservice pattern. Now there is a challenge. We need to be very cautious when creating branches, else both functionality and performance will be affected, right? So we need to create branch as per the need of functionality or as per the result required by the business. Else the result will not match as per the functionality, right? And so far as performance part is concerned, we need to be very cautious if any chain is not impacting the turnaround time, right? If possible, make it parallel processing and try to make small change in this branch pattern. The last pattern under this category, that is client-side UI composition pattern. This is the pattern to solve problem of how to implement UI page which displays data from microservices. UI composition microservice would be similar to small API gateway, but in this case each one is responsible for small UI area. Yes, so why it is small API gateway? Because in particular UI area, the set of microservices call are consolidated, and with the service will be available, all the service will be available with respect to the need of that particular area, right? This design pattern is considered at client side and not at server side. Please mark, this is not going to be implemented at any server side component. It is supposed to be a client side component or client side module, right? Each UI page has different component like header, footer and other component in remaining page of area, right? With respect to each component, aggregation of microservices is carried out, right? For example, for header part, it requires 3 to 5 microservices with respect to the rendering data on header. So clubbing of these 3-4 microservices done at client side with respect to called to the server, right? This aggregation happens at client side, and methodology of aggregation depends on the tool is selected. Perfect. So the tools I mean to say, whether you are whether we are picking EXT.js, whether we are picking Angular or any other UI tool. So strategy or this design pattern will be considered with respect to the tool, how tool is going to implement this design pattern, and it is with respect to implementation of tool. This design pattern gives flexibility to UI implementation if any change is anticipated. So this is the benefit of this pattern. Strategy of composition in context of UI component should be done wisely, and right tool selection required to be reduce the complexity. Yes. So again, the clubbing of microservices has to be very wisely. So we need to be sure with respect to the component on UI part and associated services of requirement of that component. Once that is clear, then we need to implement right clubbing strategy for that component. Right tool selection is required. As I mentioned earlier, that implementation of this design pattern depends on the tools which we are selecting. So we need to have right knowledge of the selected tool, as well as we need to have right knowledge of requirement of that UI component. We are done with integration patterns. Now let us move to another category of design pattern. Let us move to next category of design pattern, that is database pattern. And first design pattern we will consider, that is database per service. So what should be the database structure or architecture in microservices based application? Here let us consider we can keep each microservice data private to that microservice, and this data will be accessible only via relevant microservice. The microservice will use its own database for transaction. So here particular microservice will have particular database, and that database will be owned by that microservice and entertain the transaction through particular microservice only, right? So database per service does not always need to have separate database provision. That means it should be a private table per service, or schema per service, or database server per service, right? Now let us consider the advantages. Changes to an individual database don't impact other services. Thus, there isn't a single point of failure in application. Here we are achieving autonomy, we are achieving loosely coupled, and we are achieving isolation level implementation. This helps us to separate out or to isolate even a failure scenario also. So if one service fails, it won't affect to other service. The other advantage is the individual data store are easier to scale. So if a particular service has more number of transaction or heavy transaction, in that scenario we can scale particular database according to a particular microservice. We don't require to deal with the entire application or entire installation of application, right? So this is something flexibility or granularity of scaling, either upward or downward. The third one is we are able to use polyglot persistence over here. Now let us discuss about the challenges. As mentioned, each microservice can only access directly its own data store. Therefore, service needs to be communicated rightly with each other. That means need a communication method to exchange the data. So each service must provide a clear API, right? Here the basic requirement is a robust architecture with respect to communication between two microservices to fulfill the requirement of exchange of data. Spanning transaction across microservices can negatively impact consistency and atomicity. See, there are a lot of transactions which are involved with respect to more than one microservices. That means one transaction required to be completed or committed when more than one microservice will complete their task. So here one transaction depends on more than one microservices, right? So here if something goes wrong with respect to one microservice, then the atomicity of complete transaction will be impacted. There isn't a simple way to execute join queries on multiple data store. Yeah, this is going to be a challenge because the granularity of database is with respect to microservice, and there are a lot of chances that to access more than one table or to entertain join queries will be a challenge over here. Data related to operations spanned across the microservice could be hard to debug in case of any problem. Yes, so it is simple, it is loosely coupled, it is isolated. So when something wrong with some transaction and some inconsistency found, then it will be a challenge to understand through which microservice we have landed in trouble. Now let us move to next design pattern under this category, which is shared database per service. We can use database which is shared among microservices. That means each service is free to use data accessible to other services as well. So there is one database and n number of microservices can update or manipulate that database. A developer uses familiarity and straightforward ACID transaction to enforce data consistency. This is something advantage here it is mentioned. So with respect to transaction, if we want to maintain ACID properties, we need to remain consistent with respect to all the database update required to complete one transaction. So when we are using database per service, one transaction may have more than one microservices to fulfill that transaction, right? So more than one microservice plays a role for particularly one transaction. In that scenario, if any microservices fails, then the inconsistency will be there with respect to the completion of transaction. So there will be unfulfillment of ACID properties, right? Now, what are the advantage we can consider? There is one advantage which is very much clear. A single database is simpler to operate, right? So again, if microservices own one database, I mean to say per service, one service, one database, in that scenario, I think managing consistency with respect to failure to achieve ACID transaction property will be a challenge. Any failure in any microservices in database per service approach may affect a lot. Now let us go to the challenges. A developer working on particular service will need to coordinate schema changes with the developer of other services that access the same tables. Now this is something related to communication model across your development teams. So as we are mentioning over here that we are having one database and the complete community of microservice will access this database only. So in that scenario, any change in schema will affect or may affect the functionality of other microservices which owns some other development team, right? So in this scenario, the project management supposed to be rightly executed with respect to their communication model. So here definitely communication is very much required across the teams. Runtime coupling, because all services access the same database, they can potentially interfere with one another. Now, what does this mean? For any transaction, ACID properties has to be fulfilled. So for example, if some service locks one table to fulfill its transaction, another service has to wait with respect to completion of the transaction. Now in this scenario, waiting period increases, right? So execution of one service affects the execution of another service, right? So that is one part. Another part is there are in lot of scenarios in lot of scenarios there are chances that client will experience the phantom data. That means client will experience a data which was picked with respect to some partial update of database through another service. So this kind of challenges will be there with respect to accessing one database through many microservices. Single database might not satisfy the data storage and access requirement of all service. Yeah, that is obvious. So if we have multiple subdomains, then each subdomain will have a different requirement with respect to storage capacity as well as logical requirement of schema. So that is also again a challenge with respect to single database. The third design pattern under this category is Cqrs, which means Command Query Responsibilities Aggregation. In loosely coupled microservice infrastructure, handling complex queries to get rid of insufficient joins are uphill tasks. Cqrs offers to use separation of concern principle and separate reading database and writing database with two databases, right? So try to understand. So a client who wants to read data will fetch one database, and client who wants to write data will consider another database. So both are separate, but beauty of this is both are reading not at all a wrong data, right? We can say that Cqrs separates read and write into different databases. Command performs update data, query performs read data, right? So in one database query will be considered and another database commands will be considered, right? In order to isolate command and queries, it's best practice to separate read and write database with two databases physically. It is not that we are creating same schema or views in same database. It should be physically separated. By this isolation, we can even use different database for reading and writing database type, like NoSQL document database for reading, using relational database for CRUD operation. So see, when we are using NoSQL document database for reading, we will have very low latency to fetch the data. While we are considering relational database for CRUD operational, it is more effective with respect to transaction, right? With respect to transaction, I mean to say it can handle more number of transactions by maintaining ACID properties, right? So this is the beauty. Cqrs comes with separating commands and query database, so this requires to be sync both database. Yes, so if we are updating one database, same database supposed to be visible to another client who wants to read data. But here challenge is that both database are different. So to fulfill this, we need to implement some event-driven architecture. And with event-driven architectures, there are same new patterns and practice should be considered when applying Cqrs. So when we want to consider Cqrs, we need to consider some other approaches also to fulfill the need of this design pattern. So let us understand the advantages. Cqrs allows the read and write workloads to scale independently, right? Yeah, so there are some applications which are more intensive with respect to write. There are some applications which are more intensive with respect to read. So we can strategize scaling with respect to such kind of requirement. So if you want, so it is not that we want, so it is not that to address scalability with respect to read, we need to scale up a database which is responsible for write as well, right? So here, if your concern is to improve performance for read, then scale up read. If your requirement to address more transaction, you can upgrade database with respect to write or with respect to command. The read side can use a schema that is optimized for query, while the write side uses a schema that is optimized for updates. That is what I have explained you, right? Segregation, the read and write side can result in models that are more maintainable and more flexible, right? So here again, we know the requirement of read, we know with respect to the requirement of write, right? So we can define a separate strategy with respect to both database. So we will not have any kind of ambiguity that okay, if we are making some change, then capacity of reading will be affected, or if we will make some change, then capacity of write will be affected. So here it is not like that. We have narrowed down our purpose with respect to the maintenance approaches. By storing a materialized view in the read database, the application can avoid complex join when querying. Yes, so here we were facing challenges in database per services with respect to implementing complex queries. So when you implement materialized view within database, then microservice need not to bother about any complex query. It just need to call that view and fetch the data. Now let us understand some challenges. Supporting Cqrs pattern requires expertise in variety of database technologies. Yes, we have introduced two databases here with respect to reading and with respect to writing. So obviously we need to take care of different variety of database, and that make us either extra cost or more effort with respect to managing. Ensuring data consistency requires special consideration in terms of service level agreement. Yes, here a service level agreement again differs with respect to reading database and writing database, right? So if challenges are there with respect to updating database, then our SLA will be different, and challenges with respect to reading the data, then our SLA is supposed to be different. And the another part is that we should be enough cautious that with respect to syncing both the data. So once some database got updated, within fraction of time that should be visible to the client who wants to view that data in particular database. So that's the thing. The next design pattern is event sourcing design pattern. Event sourcing is a great way to automatically update state and publish event. Event sourcing uses a radically different event-centric approach to persistence. A business object is persisted by storing a sequence of state changing events, Whenever an object state changes, a new event is appended to the sequence of events. Events are persisted in event store. The event store not only acts as a database of events, it also behaves like a message broker. It provides an API that enables services to subscribe to events. Each event that is persisted in the event store is delivered by event store to all interested subscribers. The event store is a backbone of an event-driven microservice architecture. So please mark here, we are talking about storage of events state, as well as we are publishing some events with respect to that state. Here let us consider example with respect to Cqrs implementation. In Cqrs implementation, we have considered two databases, where one database was considered for write operation, another database was considered for read operation. For each write operation, read database has to be updated instantly. So now once the state of write database changes, the event to update read database will be triggered. So thus this functionality can be achieved through event sourcing implementation. Now, what are the benefits? Auditing functionality is often added as an afterthought, resulting in an inherent risk of incompleteness. With event sourcing, each state change corresponds to one or more events, providing 100% accurate audit logging. Because event sourcing maintains the complete history of each business object, implementing temporal queries and reconstructing the historical state of entity is straightforward. That means it gives robustness with respect to the data retention. Now, what are the challenges? Requires an extremely efficient network infrastructure given the inherent time sensitivity of the pattern and susceptibility to potential latency issue. What does that mean? Actually, once we are changing the state in event store, new events are getting triggered. The response to this new event has to be immediate, and this is the place where the risk of latency is there. So to mitigate this risk, we need to have efficient network infrastructure which can respond the events. Second one, requires a reliable way to control message formats, for example using a schema registry. Yeah, so standardization is required with respect to message format, and this format has to be valid for all the microservice to understand, or all the message brokers to understand. So if we are using Kafka, if we are using RabbitMQ, then message format should be in such a way so that such message broker can absorb the event and execute the required task or trigger the required task. Now, next is the last design pattern in category of database patterns, which is Saga pattern. The Saga pattern provides transaction management using sequence of local transaction, right? So a local transaction is the atomic work effort performed by Saga participant. So it's a set of microservices who are responsible to perform individual atomic transaction, right? And aggregation or collating all this microservices by maintaining successful transaction is the target of this design pattern. Each local transaction updates the database and publishes a message or event to trigger the next local transaction in the Saga. As I mentioned, in this design pattern or in transaction, there are more than one microservices are playing their role, right? So to complete the transaction, after completion of one microservices task, there is requirement of triggering another microservice to fulfill the another task. If a local transaction fails, the Saga executes a series of compensating. You might recall the rollback mechanism in monolith implementation or in a simple RDBMS database, right? So for example, if in sequence of microservices where transactions are getting executed, even if one microservice fails, we need to have series of microservices according to need of functionality for compensating that transaction, right? I mean to say, it will undo the change. There are three types of transactions so far as Saga design patterns is considered. One, compensable transaction, which are transactions that can potentially be reversed by processing another transaction with the opposite effect. That means if you are inserting, the opposite effect is deleting. So this kind of approach. A pivot transaction is the go or no go point in Saga. If pivot transaction commits, the Saga run until the completion. A pivot transaction can be a transaction that is neither compensable nor retriable, or it can be the last compensable transaction or the first retriable transaction in the Saga, right? Yeah, this is something interesting. Retriable transactions are the transactions that follow the pivot transaction and are guaranteed to succeed. Yeah, right. So in Saga pattern, there are two approaches are considered. One is choreography. Choreography is a way to coordinate sagas where participants exchange the event without centralized point of control. Right? So each microservice calls the another microservice after completing its task by its own. There is no centralized mechanism where after completion of one microservices, the responsibility will be delegated to another, to a centralized system to call another. It is not like that. Microservices themselves are responsible to do that. Orchestration. Orchestration is a way to coordinate sagas where a centralized controller tells the Saga participant what local transaction to be executed. So it's different than choreography. Here we have some centralized mechanism. So once one microservice completes its task, it goes to this centralized system, and that system will decide which microservices required to be called next. Now let us try to understand the advantage of Saga patterns. It ensures data consistency in distributed system without tight coupling, right? So if we want to achieve some transaction, that transaction supposed to be consistent with respect to, you can say, asset properties, right? It should be atomic, it should be atomic, and it should provide the surety of completion of transaction rightly. Second one is rollback or compensate if one of the operation in the sequence fail. Yeah, so as we have mentioned, there are set of compensating microservices, right? So those microservices take care of this task. If something fails, then they execute the reverse operations. What are the challenges or a disadvantage? Not advisable for tightly coupled transaction. Yeah, it is obvious, right? Not suitable for compensating transaction that occurs in earlier participant, right? So if something went wrong in sequence, three microservices prior to three microservices in sequence, that in that scenario there is probability of failure in rolling back the transaction. So this is some challenges, but strategically we can handle this thing. Not suitable for cyclic dependency. Yeah, that is agreed. Yeah. We have reached at the end of all the database patterns. Now it's time to move to understand another category of design patterns. Next category of design patterns is observability pattern. Now let us discuss the first design pattern, log aggregation. Microservices generate and store logs individually within their isolated environment. This can make it difficult to audit or report on solution-wide log data that spans multiple microservices. Means it is a distributed system when we are thinking about microservices, and deployment of microservices are at different location on different servers. So a special aggregator component is utilized to connect each microservices and collect its log in order to store them in a central repository. So as per our need, we need all the logs at some central location so that we can analyze and we can understand the state of application holistically. Such implementation should be in the form of service, right? So to collect all the logs at one location should be a responsibility of service. It should not something else. Users should be able to search and analyze the log provided by this logging service. It is required to visualize this log in a way so that holistic information of application execution can be captured in real time. So it is immaterial whether we are collecting all the logs and putting it at centralized location. It will be useful if and only if we can visualize it in a way so that we can take the decision with respect to the current state of application or complete architecture. Log aggregation tools leverage correlation ID, and we use a single ID for related set of service call. Yeah, that is obvious because each log requires some ID to understand the source of log with respect to the instance of microservice as well as the pod where the microservice is deployed. With the help of messaging tool, dynamically logs are stored at centralized location and visualized with the appropriate tool. Yeah, so generally the approach of messaging tool is considered. So once log is generated or log is updated, on the basis of that event, messaging tool triggers task of moving logs from at particular location to the centralized location, right? So messaging tool generally triggers the service which picks the log and stores in on centralized location. Now what are the advantages? This approach helps to manage continuity of application by visualizing of functioning and malfunctioning element. So we will understand the application status, if it is working or even if it is not working, or it is working in incorrect manner. What are the challenges? This is a non-functional implementation, so can be considered as a cost, but we do not have option than this. Until unless we cannot keep track of our application, we cannot manage the application rightly. Let us move to the next design pattern. That is performance matrix. Microservice architecture structures an application as a set of loosely coupled microservices, and each microservice can be deployed independently in agile manner to enable continuous delivery and deployment. Now, answer of how to track application performance and check bottlenecks is must to manage the continuity of application. Right? This is a non-functional requirement, but you cannot get rid of this. As a part of solution, there is a need of instrument a service to gather statistics about individual operations, aggregate metrics in centralized metrics service which provides reporting and alerting. So here also we are going to depend on a service which can gather such kind of matrices and keep that matrices on centralized location. Now there are two models for aggregating such matrices. One is push. The service pushes the matrices to the matrices services. So source is pushing such values to a service which is responsible to collect these matrices. Pull mechanism. The matrices services pull the matrices from the service. Here source service has nothing to do. There is a one service which periodically picks the matrices, not periodically, even instantly picks the matrices with respect to the performance. Now API gateway is the place from where the health check is required to be done, and normally such tools are configured at API gateway level only, because all the endpoint starts from API gateway and health check has to be start from entry point itself. Now let us understand the benefit of this design pattern. Through this matrices, continuity of application can be maintained and strategy for scaling up or down can be defined. So it is obvious, if health is not correct with respect to any microservices, we need to implement the corrective steps. So those can be scaling up with respect to processing capacity, storage capacity, or handling traffic. So this can be done with respect to such these matrices. This is a non-functional implementation, so can be considered as a cost. Yeah, it's a cost, but do we have any other option? Next design pattern, distributed tracing. How to understand the behavior of an application and troubleshoot problem. This is the problem what this design pattern addresses. Distributed tracing, sometimes called distributed request tracing, is a method to monitor application built on a microservice architecture. Each external request is assigned a unique ID and tracked as it flows from one service to another on a centralized server that provides visualization and analysis. So this unique ID will flow in all the services of the path of that request, and so with the help of this unique ID we can manage to trace. Distributed tracing is the process of following a single transaction from endpoint to endpoint in context. The focus of distributed tracing is to pinpoint exactly where a problem occurred, right? So we can find the location where the problem is or where the bottleneck is. While the focus with the logging is especially what happened with the application, system administrator use logging so that they can take action to ensure application function properly. So try to understand, with the help of logging and with the help of tracing, we can reduce turnaround time of fixing any problem. With the distributed tracing, we can find the location, and with the help of logs, we can understand the problem, and accordingly solution can be implemented. Distributed tracing helps team to understand more quickly how each microservice is performing. Perfect. I have already mentioned this thing. Detect unforeseen behavior that result from automated scaling, making it easier to prevent and recover from the failure. Yeah, so again, we can plan the defect prevention with respect to understanding the location and the log. So this is something either may require to scaling, or we may require some other aspect to resolve this problem permanently. The last design pattern under this umbrella is health check. There are several scenarios when particular service is not in capacity to serve the request. Reason may be DB connection issue, service is just initialized and doing some sanity checks, or service is down. So many others as maybe. Load balancer, service registry or API gateway should not redirect any request to such failed service instance. So we need to detect if running service instance is able to take request or not. See, please understand, here what we are considering, service is running, but it is not in capacity to respond the request, right? So we can add health checkpoint to each service. This endpoint can perform following tasks to check its service health. Those are connection availability, host status, application specific logic, like that. Load balancer service registry periodically invokes the health check endpoint to check the health of service instance. On the basis of health check parameter values, load balancer will act as per the strategy defined and response will be provided to client. So here things are getting understood before even we are calling the service. So in this scenario, if service is not in capacity to serve, then load balancer can find another working similar service to cater the client. I mean to say, we can define the right strategy with respect to such scenario. Resiliency can be achieved based on health check results. So as I mentioned, if we find something inappropriate with respect to the health of microservice, we can take appropriate actions. Application continuity can be strategized, so that we can define logical response to client with respect to such unexpected health issues. So we are done with observability patterns, and it's time to move next category of design patterns. Cross-cutting patterns is the next and the last category what we are going to discuss now. The first design pattern over here is external configuration. Often services needs to be run in different environment. Environment specific configuration is required, such as secret keys, database credential, and so on. This pattern is about moving configuration information out of application deployment package to centralized location. During runtime, microservices provide an option to reload the configuration without having to start the service. So think about, if we have provided some database configuration detail and microservices running, at certain point of time we may require to change those parameters, maybe URL, maybe credential. So in that scenario, it's a costly affair to down the microservices, change the configuration detail and start the microservices. So this is not the logical approach. We need to have some automation implemented at centralized level, and which can trigger configuration upgrade automatically. In microservices architecture, we have several instances of different services. We can choose to embed the read and reload feature from the externalized configuration store in the services, or to dedicate this feature to a standalone configuration server. So choice is yours, but requirement over here is the effect of configuration supposed to be without restarting the service. So we need to have continuity even if configuration changes. Now, what we are going to achieve out of this? Less flow of exchange between the service and the externalized store. Yeah, system become independent of implementation of externalized configuration store. Standalone configuration server can use the service discovery pattern and service registry pattern to scale horizontally. Yeah, so this is something which provide the continuity of services without manual intervention, as well as low latency of executing the task. The next design pattern under this category is service discovery pattern. In order to make a request, your code needs to know the address of a service instance. For each newly created service needs to recognition from all the client who wants to use it. So if we are deploying new service, that service required recognition from all the services which wants to call this service. The service discovery mechanism help us to know where each instance is located. In this way, a service discovery component acts as a registry in which the addresses of all instances are tracked. This pattern has 4 sub patterns, and they are: first one is self-registration pattern. A service instance invokes a service registration API to register its network location. It may also supply a health check URL to understand the health when service is running. Second one is client-side discovery pattern. When a service client wants to invoke a service, it queries the service registry to obtain a list of services instance. Third one is server-side discovery pattern. Instead of a client querying the service registry, it makes a request to a DNS name which resolves to a request router that queries the service registry and load balances the request. The fourth one is third-party registration pattern. Instead of service registering itself with the service registry, a third party called the registrar, which is typically part of deployment platform, handles the registration, and rest all microservices who wants to use particular service will get the information of location of service. Now, I don't think that I need to mention the advantage of this design pattern, because this design pattern automate to understand how to call the service with respect to the address of services. If we won't implement this design pattern, I think it's a huge effort of providing manually the location of microservices, and microservice architecture will no more useful with respect to the managing the infrastructure. Let us move to circuit breaker pattern. When service A tries to communicate with service B, it allocates a thread to make that call. Here there are two kinds of failures are expected: immediate failures or timeout failures. Under this condition, resiliency needs to be achieved. The circuit breaker concept is straightforward. It wraps a function with the monitor that tracks the failure. The circuit breaker has three distinct states. Close. Here all requests are allowed to pass to the upstream service, and the interceptor passes on the response of the upstream service to the caller. Here the tracker will not will provide the status of healthy next microservices, so that the current service is enough comfortable to call the next service, and the circuit is considered as a closed circuit. Now open circuit. No requests are allowed to pass to upstream, and interceptor responses with the default response, generally an error response. So what is open state? Open state means the no request is allowed further. That means service has already registered that the next service is not working or not in operational state, so there is no benefit of calling that service. So in that scenario, either I need to provide a response which is strategically defined, or I need to provide an error response. Perfect. Now half open. Some of the requests are allowed to pass to upstream, others are terminated and responded with the default response. The intention of this half open state is to periodically verify whether the next service is ready to serve or still it is in problem state. Now, so once particular number of calls get succeeded, I mean to say there is a threshold is defined with respect to the success rate. If that is achieved, in that scenario the half open state becomes the closed state and traffic will move as a normal scenario. There will be no restriction in calling the next service. Now in same way, the lower threshold is also defined to convert half open state to open state, right? So once that lower once unsuccessful rate goes lower than the particular threshold, then half open state will convert to the open state and current service will not allow to call the next microservices. This is the overall mechanism of circuit breaker pattern, and this is very important design pattern to maintain resiliency in microservice architecture. Now it's time to discuss our last design pattern, which is blue-green deployment pattern. It is difficult to maintain business continuity along with new feature development or maintenance activity. This is a deployment strategy in which you create two separate but identical environments. One environment is blue, which is running the current application version, and one environment green is running the new application version. At any time, only one environment is live. With the live environment, all the production traffic getting served. As you prepare new version of your software, deployment and final stage of testing takes place in environment which is not live. That means green environment, which is not catering the request of client. Once you have deployed the fully tested software in green, you switch the router so your all incoming requests now go to green instead of blue. Now green is live, blue is idle. What does that mean? So now the environment which was green earlier, now it is blue, and environment which is blue earlier, now it is green. So they have toggled their state. So now whatever the new features will be introduced in feature, that will be deployed in current green, right? So this way this design pattern works. This technique can eliminate downtime due to the app deployment. So this is the advantage of this pattern. It has huge associated cost with respect to having two parallel environments. Yeah, agree on that part, but to maintain the disaster management or to maintain the business continuity, we need to manage such environments. That's the end of all the design pattern for what I was intended to discuss. We have completed all the design patterns under mentioned 5 category of design patterns. Believe me, we have discussed 26 design patterns today, and they are decomposition patterns, integration patterns, database patterns, observability patterns, cross-cutting patterns. Great. Think we have learned a lot in today's webinar. There are several tools exist in market. Below is a list of few tools which fulfills need of some of design patterns which we discussed. Please mark, I haven't included all those design patterns which are in nature of purely strategy, where there is very less scope of technology, and these tools are great. So I'm done with today's webinar. Before we close, we understand what we have done. We have discussed 26 design patterns. We have covered theoretical aspects of all design patterns. The intention of this webinar was to introduce with design patterns of microservices. The implementation part of design pattern was not covered due to the time constraint. Information related to tools in context of design pattern will help you to make right pick for implementation. Thank you very much, and definitely we will meet again. My contact details are, as far as email part is concerned, abhigna@noldus.com, and here I have also mentioned my LinkedIn profile.